Okay, so in this video we're going to take a look at problem number 11. It states that if the volume V equals S cubed of an expanding cube is increasing at a constant rate of 120 cubic inches per second, how fast is the length S, right, looks like a 5 but it's an S, of the sides increasing when the volume is 8 cubic inches? Well, this is a related rate problem. From this word problem, I can extract the following information. We know that for a cube, we know that the volume, V, is equal to S cubed. We know that we're giving a constant rate. Well, it's 120 cubic inches per second. Since it's given to be cubic inches per second, then that tells me that the rate of change, or the rate at which volume is changing with respect to t, right? Remember we use the symbol dv dt to represent a rate of change. Well, since it's increasing at a constant rate of 120 cubic inches per second, I can say that dv dt is basically positive 120. If the expanding cube was decreasing, or if it was a de-expanding, if that's a word, if the cube was not expanding at all and it was decreasing at a constant rate, then this value would have been negative. So we're given v is equal to s cubed, dv dt is equal to 120 cubic inches per second. What we want to figure out is how fast is the length s, so we're trying to find the change of our side s with respect to t, so ds dt, when volume v is equal to 8. Well, first of all, what we need to do is first figure out what will be the value of s when v is 8, right? So first, find the value of s. Well, in this case, since volume is equal to s cubed and volume is equal to 8, then that implies that 8 should equal to s cubed. Well, if I take the cube root of both sides, cube root, then we're going to get that s is equal to 2, or 2 is equal to s. So we know that now for our expanding cube, we're trying to figure out the rate of change when s, your side, has a measurement of 2 inches. So now we're going to basically apply our one step of calculus. That is, we want to create an equation where we have a relation between the rate of change of volume and the rate of change for our side. Well, that means that I need to take the derivative of our given equation, v equals s cubed, with respect to t. So we're going to find the derivative of v equals s cubed with respect to t. So we're basically applying an implicit differentiation here. So we have d dt of v equals s cubed. Well, if we take the derivative with respect to t, we're going to get dv dt is going to equal to, well, take the derivative of s cubed with respect to t, you're going to get 3s squared ds dt. So in this problem, we're trying to find ds dt, and we now know that, well, if we use all the prior information, we could just plug things in. So we're going to have the following. Well, dv dt, this is equal to 120 So we're going to have 120 equals 3 times s squared. Well, s was given to be 2. So we're going to have 3 times 2 squared ds dt. So I'm going to simplify this equation, or just simply isolate ds dt by itself. Well, we're going to have 120 equals 3 times 2 squared. Well, 2 squared is 4, so 4 times 3 is 12. So it's 12 ds dt. And if I divide by 12 on both sides, I'm just going to rewrite this the other way. We're going to have ds dt is going to equal to 120 over 12. Well, 120 divided by 12, that's going to be 10, and we just need to figure out the correct units. Since we were giving inches and second, this is going to be 10 inches per second. So that'll be your final answer. So how fast is the length s of the sides increasing when the volume was exactly 8 cubic inches? Well, when the volume is exactly 8 cubic inches, we know that our side, s, is going to be 2. And the rate at which it's increasing by is going to be 10 inches per second. And that's it for number 11, our problem on related rates. Okay, on to problem number 12. It states, find where the graph of y equals x cubed minus 6x squared is concave up, concave down. Find all inflection points. So, what we're going to do is, first of all, find the first and the second derivative, right? We're going to apply our test for concavity. So we'll have the following. Since y is equal to x cubed minus 6x squared, then we know that the first derivative, y prime, is going to equal to 3x squared minus 12x. Now we want to find our second derivative, y double prime. So y double prime is going to equal to 6x, right? Derivative of 3x squared is 6x, and the derivative of negative 12x is negative 12. So now that we have our second derivative, if you want to find basically the possible inflection point, you can set the second derivative here, in this case, equal to 0. Other cases, you would have had to check where the second derivative will not exist. But in this case, since we're dealing with a linear equation, you know that for every value of x, you're going to get back an output value for your second derivative. So just set the second derivative equal to 0. So we have 6x minus 12 is equal to 0. If you add 12 on both sides, then divide by 6, you're going to get that x is equal to 2. So x equals 2 is a possible inflection point. If you want to really determine if it is an inflection point, that's where we need to test for concavity. At which interval is the function going to be concave up and concave down? If concavity changes within the intervals, meaning to the left of x equals 2 and to the right of x equals 2, then you know that this will be indeed an inflection point. So here's where we create our table, right? So again, just a recap, we found the first and second derivative, set the second derivative equal to 0, and now we create our table. So since I have one inflection point, then that tells me that I'm going to have 2 intervals. So when we create our table, we're going to have intervals. We know that, again, since it's one possible inflection point, then there's only going to be 2 intervals. So it's going to be from negative infinity to 2, and then from 2 to infinity. Now we need to choose our test values for each interval. So again, you just want to choose test values that are convenient. So in this case, I'm going to use 0, since 0 is within negative infinity to positive 2. And now from positive 2 to infinity, I can use a number like 10. Again, you don't have to choose exactly the numbers that I chose. I just chose something that's convenient. Now we need to determine the sign of y double prime. So we want to plug in our test values into our second derivative. So since y double prime is equal to 6x minus 12, I was going to use this notation, y double prime of 0 and y double prime of 10. So again, I just want to plug in both 0 and 10 into my second derivative. What we're going to get is 6 times 0 minus 12. Well, 6 times 0 is 0. So when you take 0 minus 12, you're going to get negative 12. So because we have negative 12, we know that this is going to be less than 0. Hence, the function, if we want to make our conclusion about this first interval, we can say that it's going to be concave down. When we plug in 10 into our second derivative, then 6 times 10 is 60. So 60 minus 12, that would be 48, right? So that's a positive number. So that's greater than 0. So we know that it's going to be concave up in the second interval. So what we have is the following. We have that the function, or our equation y equals x cubed minus 6x squared, is concave down. Right, I'm just writing this all out in plain English for us. It's concave down on the interval, or in the interval, whichever sounds correct, on the interval negative infinity to 2, and from 2 to infinity is going to be concave up. So since concavity changes from the left and to the right of 2, we know that x equals 2 will indeed represent an inflection point. So an inflection point occurs at x equals 2. Well, if you want to figure out exactly what that ordered pair will be, then you can plug 2 back into your equation. So if we were to plug 2 back into our equation, spelled namely wrong. I think I still spelled it wrong, but that's okay. Namely, if you plug 2 back into your equation, then you're looking at 2 cubed, which is 8. 2 squared is going to be 4, so 4 times 6 is 24. So 8 minus 24 is going to be negative 16. So you have an inflection point at exactly the order pair of 2, negative 16. And that's it. In the next video, we're going to look at problem 13 and 14.